Hello and welcome. So, I want you to imagine a team of computers, right? They're all working together on a big project. But here's the catch. They don't share a common brain. So, how do they talk to each other? How do they coordinate? This, my friends, is the fundamental challenge of distributed systems. And today we're going to dive deep into the three main languages they use to get the job done. Okay, so here's our roadmap for today. We'll start with what's called the decoupled message. This is for when systems are kind of doing their own thing on their own schedules. After that, we'll switch gears completely and look at the continuous stream, where, timing is everything. Then we'll tackle the big problem of how to send one message to many systems at once. And finally, we'll wrap it all up with the key takeaways you need to remember.
So let's really get into this. When you have every computer acting on its own, communication becomes the absolute lifeline that allows them to collaborate. But, and this is the crucial part, there is no single best way for them to talk. The choice of communication style is a huge design decision. It's one that's going to directly impact how reliable, how fast, and how flexible our entire system will be. So yeah, it's a big deal.
All right, let's begin with our first style of communication. Imagine this scenario. You need to send a really critical piece of information to another system, but you have absolutely no guarantee that the receiver is online right now. How do you make sure your message doesn't just vanish into thin air? Well, the answer lies in something we call message-oriented communication. The solution here is a type of system called Message-Oriented Middleware, or MOM for short. Now, the key idea is this logical contact point. It's very different from a direct phone call, what tech folks might call a remote procedure call or RPC, where you need to know the receiver's exact address and they have to pick up. Instead, MOM acts as a trusted go-between. The sender simply hands off the message and the middleware takes on the full responsibility for getting it delivered. And this really is the magic of it all, decoupling. Just think of it like an email system, or even the good old postal service. You can write and send an email at 3 a.m., right? You don't need the other person to be awake and staring at their inbox waiting for it. The email system stores it and delivers it when they're ready. This is what we call asynchronous communication, and it gives us a tremendous amount of flexibility. So, how does this actually work under the hood? It's a really simple but very powerful three-step dance. First, the sending application takes its message and puts it into a queue. Think of it like dropping a letter in a mailbox. Second, the middleware, our post office, reliably stores that message. This is the crucial store and forward step. It's safe. Finally, whenever the receiving application is ready, maybe it's minutes or even hours later, it just connects and pulls the message from the queue. This model is just perfect for applications that aren't running at the same time.
Okay, so what's the catch? There's always a trade-off, isn't there? As you can see, the big advantages are incredible reliability and flexibility. The system handles the hard work, but that power comes with its own set of challenges. Setting up these systems, things like IBM's WebSphere MQ, for example, can be pretty complex. And if you have a huge system, manually configuring the whole network of queues and routes can become a real administrative headache.
All right, now let's shift gears and look at our second communication style. So far, we've talked about messages where timing isn't a huge deal. But what if the timing of the information is just as important as the information itself? I'm talking about things like live audio, a video conference call, or real-time data from sensors. In these cases, a delay or a message arriving out of order can completely ruin the experience.
And this brings us to stream-oriented communication. The key concept here is that there's a temporal, or time-based relationship between the messages. The data isn't just a series of independent letters anymore. No, it's a continuous flow, just like water rushing through a pipe or a conversation on a telephone. The timing, the rhythm, the space between the packets, all of it matters.
And this slide really puts it into perspective, right? It's a direct contrast between the two models. With message-oriented communication, the time between messages doesn't really matter. But for streams, it is absolutely critical. Think about it. An email arriving 5 minutes late is usually fine, but a 5-minute gap in the middle of a phone call? That's a completely different story. This intense focus on time is what defines stream-oriented communication. But there is a huge challenge here. You see, most networks, including the internet, operate on what's called a best effort basis. That means they try to deliver things on time, but they make no guarantees. And this creates a problem that I'm sure we've all experienced: jitter. Jitter is simply the variation in when data packets arrive. Sometimes they're early, sometimes they're late. When jitter is high, that's when you get that choppy audio or that glitchy, pixelated video because the data just isn't flowing in a smooth, predictable way. So how do we fight this? How do we solve for jitter? Well, the solution is actually quite elegant. We use a buffer on the receiver's end. I want you to think of this buffer as a small reservoir of water, or maybe a shock absorber in a car. It collects the incoming packets, which might be arriving all erratically, and then it releases them to the application at a perfectly smooth, constant rate. This is exactly why your online videos sometimes buffers when it starts. It's filling up that little reservoir to protect your viewing experience from all that messy network jitter.
Okay, time for our third and final style. We've looked at one-to-one communication, both when time doesn't matter and when it's critical. But what if you need to send the exact same piece of information to a huge group of recipients? 1,000? 1,000,000? Sending a separate individual copy to each one would be, well, it would be incredibly inefficient. You could easily crash your network. This is exactly the problem that multicast communication is designed to solve. And the simplest way to think about it is a radio broadcast. A radio station sends out its signal just once, right? But that single transmission can be picked up by thousands, even millions of listeners simultaneously. Multicast applies that exact same brilliant principle to data networks. One sent, many receives. It's all about efficiency. So how do we actually do this at the application level? Well, there are two main strategies. The first is to build a very organized tree structure. A message starts at the root of the tree and is then forwarded down through the branches until it reaches every single member. It's very orderly. The second approach is, frankly, more fascinating. It uses what are called epidemic or gossip protocols. In this model, nodes just talk. They randomly exchange information with their neighbors, and the update spreads through the network just like a virus or a juicy piece of gossip, reaching everyone with surprising speed. And this brings us to a really crucial point about the power of these gossip protocols. This quote here highlights their incredible scalability. It says that spreading an update to all n nodes takes O log of n, that's big O of log n, rounds. Now, what does that mean in plain English? It means that even if you have a massive system, an update can spread to every single node in logarithmic time. To put it another way, doubling the number of computers in your system doesn't double the time it takes for a message to spread. It just adds one tiny constant step. This makes gossip protocols extremely efficient for very large, very dynamic systems. So, there we have it. We've explored three very distinct styles of communication in distributed systems. Let's take a moment to summarize and really see how they all fit together. I think the biggest takeaway here is that choosing the right communication style is a fundamental, absolutely critical design decision. There's no one-size-fits-all solution here. It's all about picking the right tool for the job. So, let's bring it all home with this final comparison. The best way to think about this is like having a toolkit. For situations where you need reliability but time isn't the main concern, you're going to reach for message-oriented communication. That's your email. Now, when every single millisecond counts, like with streaming media, stream-oriented communication is the tool you need. That's your phone call. And finally, for maximum efficiency when you're broadcasting information to a large crowd, multicast is really the only way to go. That's your radio broadcast. Each one is a specialized solution for a very different kind of problem. And that leaves us with one final thought to ponder. We've talked about these as three separate, distinct styles. But of course, modern distributed systems are incredibly complex. Just think about a live streaming service that also has a text-based chat running alongside it. Right there, it's using streams for the video, but it's using messages for the chat. So the question is, how will these styles continue to blend, merge, and hybridize as we build the next generation of these massive, global-scale applications? Thanks for watching, and see you in the next session of this series.